I don't mind if you set yourself up once again with respect to your Z value, your test score. You show me this, and then you go to your calculator and get your value there. I don't mind that. Whether you do the actual calculations with it, or you show, or just go to your calculator, type the information into your calculator, and come up with your Z-score that way. That is fine. But what I also need to see with this, need to see if it's a right tail test, what is my critical value here? Okay, taking this value right here, where am I at? Or if you have a p-value, if you calculate your p-value and use your calculator to find your p-value, you calculate that there. Then you go, is p greater than this alpha value, or is this p less than this alpha value? And we reject or fail to reject. Either one is correct, and I will accept either one. You need to find something that works for you, I guess, something that works for you. Traditionally, what I like is this first way right here, because it gives you a visual with respect to a z values, and everything's based on a z value here. But if you go into the p world and deal with the p value is less than or greater than the alpha value, that's fine also. Whatever works for you. Find something, find a niche that's good for you. Questions about anything else with respect to hypothesis testing? We've been basically on that same worksheet for about 4 days. We did what's a null and alternate hypothesis, one tail, two tail. Then we went into actual calculations with it, doing a z-test value, and then we went into calculating a p-value. So we've been working with the exact same problems. Is there anything else that you need me to go through in regards to the problems on that worksheet? Hopefully, as you go through them, as a lot of times, once you do one or two of them, you pretty much have done them all. Problem number 2 takes a little bit of time entering all your data values in. Problem number 2, I get that there's some data values that are sitting there, and what I will do with you will have one calculator value on your next test, but I will do it with a t value, which we will go through today, because when you're dealing with a t value, your sample size is smaller, so you're entering less numbers in. That makes it a little bit easier for you. All right, today we will be dealing with a t-test. And this is going to be very similar to a z-test. Just like when we were dealing with confidence intervals, and we were dealing with z-values and confidence intervals, then we went to t-values with the confidence intervals, and it was basically the same thing. The only thing that was different was you were pulling a value from the t-table with a degree of freedom. That's going to be the exact same thing here, except you're going to be pulling a value from your t-table for your critical values. Now, would that be a hypothesis testing, Mr. McFerrin, with an alpha value?
It becomes a theory or a law.
Is that
it's just an hypothesis. I mean, we can test it out if you want, but just because it works doesn't mean that it's a theory.
With an alpha value of 0.01 there.
Alpha value, but you also have to weigh that against the omega value as well.
That's true. I mean, we don't go quite into omega here. I know that's stats too. Now, if you talked about a beta value there,
beta.
Yeah.
I know what a beta fish is. One of those.
There we go. You know what? We had the same beta fish 5 times because it kept on dying and our kids were little. So we kept on replacing the beta fish. We'd go buy another one, we'd throw it in there, and that one would die. And then find another way, find that one floating, and we go find another beta fish and we throw another way. Yeah, our kids really
Look at
never
that.
knew. Yeah, we had quite a few Wandas. A fish named Wanda. Should be a story or something like it there. A movie about that. A musical. Anyways, once again, that circle around thing for me. Today we're going to talk about a t-test. And the t-test is exactly the same as a z-test. We will go through the exact same process, but the only difference between a z-test and a t-test, once again, is what happens when we have a smaller size. So when you're dealing with a t-test, it's a statistical test for the mean of a population, and it's used when the population is normally or approximately normally distributed. Which would it be? Distributed or distributed? Where's that accent at? Where's Mr. McFerrin at when you need it? See, accent, English term. We could debate that one, yeah. We go the math mind against the English mind. Who do you think's going to win on that one? Old man versus not as old man. A statistical test for a mean of a population is used when the population is normally or approximately distributed. Sigma is unknown, which standard deviation is unknown, and our sample size, n, is less than 30. Just like when we dealt with confidence intervals. When we dealt with confidence intervals and we had a sample size less than 30, we had to do some juggling with respect to our coefficient that we added to our sigma divided by square root of n, or multiplied by sigma divided by square root of n. That's the exact same thing here. This will change basically our critical values. Degree of freedom. Once again, how do we find out degree of freedom, Kyrie? There we go. Our sample size minus 1, our degree of freedom. Our sample size minus 1. The traditional t-test is the same as a z-test, except for the population is smaller. What this does, it changes our critical values, which will be dependent on the degree of freedom. So the critical values that we will calculate is now dependent on our degree of freedom. We still have the same scenarios. You're still going to get a bell-shaped curve. If you have a one tail left, we're still going to get a critical value here, but now it's dependent on the degree of freedom. We have non-critical and we have critical. But now we have a t-test value. Our t-test value is calculated the same way. Our t-test value is calculated the same way. X bar minus b divided by standard deviation divided by square root of n. We can also deal with a p-value here, and we'll talk about your calculator here in a few minutes. We can find a p-value and evaluate our p-value. Is it bigger or smaller than our alpha value? And we can still look at our p-value here. All things are going to be the same. Okay, we're going to go back to this exact same problem we had before, but we're changing the sample size. Okay, study found that the average stopping distance of school bus traveling 50 miles an hour is 264 feet. Group of automotive engineers decided to conduct a study of 20 buses. Average stopping distance 262.3. Standard deviation is 3. Tesla claimed the average stopping distance of the company's buses is actually less than the 264. We go back to our null and alternate hypothesis. Once again, what is established here? Our established value is 264. That's what we are testing. We may not believe the 264 is correct. We feel, because the buses and what we have done with the buses, we may have changed the engineering of the buses so that the buses can stop that. The brakes work better with the buses. My reaction time in regards to me hitting the brake pedal and the bus slowing down is a little bit different. Okay, from when I hit the pedal to when it starts to slow, it starts slowing a little bit faster and maybe a little bit more powerful there. So I can slow it a little bit quicker. So we have a mu, our null and alternate. What do we have with the null and alternate? Paige, what do you have?
Null is less than 264.
Now what
I meant, my bad. Null is greater than or equal to.
Okay, greater than or equal to 264, and the null would be what then? And once again, we would start with an alternate, and typically that's why I suggest you start with the alternate. What do we hope is true? What do these engineers hope is true? They hope what is true, that it's less than the 264. That's what they hope is true. And then the null is going to be the opposite of that. So we have mu is equal to 264 feet. We have an n, a sample size of 20. We have the average stopping distance of those 20 buses is 262.3. The standard deviation is a value of 3. And we have an alpha value of 0.01. Johanna, what would be our degree of freedom? For our sample size is 20, what's our degree of freedom?
N minus 1.
Our sample size is 20, what's our degree of freedom? There you go. We have a value of 19. So we go to our bell-shaped curve. One tail or two tail, Odessa? One tail, left or right? That's correct. We look at our alternate hypothesis. Now tell us whether we're going to be left or right. So now we have to find our critical value. We go to our t-table. We look at the one-tail row. We go to our alpha value of 0.01. But now we drop down to just our degree of freedom, which is 19. Okay, we don't go all the way to the bottom to the 2.326. That's if it was a z-score. We stop at a degree of freedom of 19. Jaden, what do you come down to? Negative 2.539. And he did good by throwing the negative with that because we're dealing with a left tail test. We have 0 there. So now we have a test value. Value minus mean divided by standard deviation, square root of n. So our x bar is 262.3 minus 264. Standard deviation is 3 divided by square root of 20. Once again, if you want to type it all in, you can type it in, but make sure you quantify, and this will give you a parenthesis there too. Janae, what do you come down to? Negative 2.534, which is sniffing at, but not quite there. This is non-critical. This is critical. We are still in a non-critical region. Not by much, but we're still in a non-critical region. So we fail to reject the null hypothesis of stopping distance of 264 feet. But once again, these are engineers. Sample size of 20, not very big sample size. I'm really close to rejecting that null hypothesis. I'm not quite there. I failed to reject it. Do I accept it? Probably not, because I'm really close. That's where a group of engineers say, we got to do this test over again. We're going to do this. We're going to do this again and measure this again because, you know what, we're close to rejecting this, but we don't have quite enough information to reject it. Now, if we go to our calculator, we go to our calculator, let's go to our t-test, our stats. Let's go over to tests, but now let's go to option number 2, which is a t-test. That is a t-test. Okay, do I have data or do I have statistics? Well, I have data here. So I'm going to go with the data. Our mu naught is 264. So I'm typing in 264. Oh, I'm in stats, my bad. I want to go over to stats. There we go. So go back up and just hit stats. My mu naught is 264. Our sample mean was 262.3. Our standard deviation was 3. Our sample size was 20. Now down here, we want to go with the alternate hypothesis, which was the less than. So I'm going to go to my less than here, hit enter, and we go down to draw. As you can see, my bell-shaped curve gets a little bit higher here. It stretches up a little higher. But I get a negative 2.5342, okay, which is corresponding to this. I get a p-value of 0.0101. Which is greater than my 0.01, which is my alpha value. So if my p-value is greater than my alpha value, I can now once again fail to reject. But once again, this is what I would need to see here if you go that route. Or if you do this and set this all up and then go to your calculator and pull this value off, that's fine. If you do this, do it by yourself and advance yourself mathematically and your calculator, KYC, know your calculator, and give me that value and use your calculator to check, that is fine. Just a way for you to check. Okay, let's go to the back side. The average family size was reported to be 3.18. A random sample of families in a particular school district resulted in the following sample sizes. At an alpha value of 0.05, does the average family size differ from the national average? Key word in there, does it differ? Does it differ? Write your alternate and then your null hypothesis. With a differ in there, Chloe, is this what do we have with our signs then? Okay, we have not equal to and equal to. Okay, so we have mu equal to 3.18, but we don't have much more. We have an alpha value of 0.05. Grant, do we have a one-tail or two-tail? Two-tail test. We have a two-tail test. But we don't have many values here. We don't have much more. We need to know a sample size, we know an X bar, and we need to know a standard deviation. So this is where I go to my calculator once again. And enter into my list 1 my data value. Okay, so let's go to our calculator. If I have data values in my list 1, which I do, okay, I can go second and my plus button and option number 4. That clears my list. Now I go to stat and edit. My list 1 doesn't have anything. So what I want to add is all my data values that I have here. So let's add in, let's just start adding 5, 4, 5, 4, 3, 6.
How do you get to the table?
Hit your stat button. Hit your stat button. You got edit, calculate, and test. Okay, the first one is we want to edit. So I just hit edit and enter. It takes me to my table. Everybody have the data values entered? Okay, now we need to pull out one variable statistic. So let's go to my stat again. Let's go to my second option, which is calculate. Option number one variable statistic. This I can pull my X bar and my standard deviation. Once again, it's a sample S. So I have an X bar of 3.83 and 1.43. Once again, this is a sample, so I'm using my S, not my sigma, which is 1.40, 1.40. I want to use 1.43, and my X bar is 3.83. My N value is 24, hopefully. And it's 24. Sometimes I mess up here. Which gives us our degree of freedom of 23. So with the alpha value of 0.05, I have a two-tailed test. So I go to my t-table. We have a two-tailed test. So I go to my two-tail and drop that down to my degree of freedom, which is 23. Abby, what do you give for 2.069? So we have that on both sides. We look at our t-test. So we have our X bar that we got from our calculator, 3.83, minus our mu, which is 3.18. Standard deviation, 1.43. Divided by the square root of n. Once again, don't want to do our degree of freedom. We want to use n. Courtney, what do you get for test value? 2.231. 2.231. So that throws me non-critical, critical, critical, throws me out here, which puts me in a critical region, so we can reject the null hypothesis of mean family size of 3.18 people. Now, once again, let's look at our calculator. Go to calculator. Okay, let's go to stats. And once again, my t-test. But what we want to do now is we want to use our data mode. So hit your left arrow so your data is now highlighted. Okay, what it should look like, you got a mu naught, a list, frequency, less than or equal to, or calculate draw. Okay, all we have to choose or change here is our mu naught. That's our accepted value. Change that to our 3.18. Now, if you entered your data into list 1, it's going to pull the data from your list 1 for you. You don't have to enter anything else in. It already pulls the data from the list, does everything for you. We have to go down to our statement here. We look at our alternate hypothesis where we have inequality. So make sure that's highlighted. And we go down to our draw. It shows our two tails here. Here's our 2.2311, which is what we calculated. Also gives us our p-value 0.0357. Which is less than our alpha value of 0.05. So once again, utilizing that, we can reject our null hypothesis. Once again, your calculator does so many things for you. But once again, what I need to see, a bell-shaped curve. Give me that. Give me this. Or if you go this avenue right here, you need to go this. But I would be able to see critical value still here. But you can still utilize your calculator. If you give me this and use your calculator for this, that's fine. Once again, the nice thing about a t-test, it looks very similar to your z-test. The only thing that's basically the difference is you have to determine what is your degree of freedom. What is your degree of freedom? And your critical values, how you calculate or determine your critical values, change a little bit. No, we don't.
Okay.
That, what we went through yesterday is how you calculate, how the p-value is calculated, which I'm not going to require you to do. I just went through what is the philosophy behind the p-value, how do you calculate that. You would have to use that test value here go to your Z table, subtract that area from the Z table from 0.5, and since this is a two-tailed test, multiply it by 2. Okay, so that was the dominoes that fell from that. Your calculator, once again, I will allow you to use that to get your p-value. I'm not going to require you to go to your Z table, subtract your Z table value from 0.5. Okay, that's my value if it's a one-tail, or if it's a two-tail, I have to multiply it by 2. I'm not going to require that. All right, you have 6 problems here that deal with a t-test. Working through the z-test. Continue to push yourself through this. Okay, continue to push yourself. Make sure you're keeping up with the material. Questions? Okay, rest of the time is yours.